in this course how GPUs are programmed. Professor Mutlu is not here. He's traveling, giving a talk. Tomorrow we won't have a lecture, but what you're going to do is watching a video that we are going to release in the website. We will make it available probably today or tomorrow, and you can watch it yourself. It's related to memory coherence, memory consistency in multiprocessor environments, related to what you were, the Professor Mutlu, what was explaining last week. So, yeah, so this is what we are going to talk about today, GPU programming, and this is the agenda for today. Let's say that the lecture is going to be divided into two main parts. Probably most of the time we will spend it on the first part, where we are going to discuss the traditional approach to programming GPUs for general purpose processing. And if we have time, probably we will have time at least to start with this second part. We will talk about collaborative computing. It's let's say a more modern way or approach to program heterogeneous systems containing CPUs and GPUs or other types of devices. In this first part, we say that we are going to consider the GPU as an accelerator. First, we are going to talk about the bulk synchronous programming model. We will see what's the typical program structure for GPU programming, and then we will go to specific considerations in the memory hierarchy. As you can guess, memory is also, or the access to memory is also going to be here, like the main bottleneck in GPUs, same as in CPUs. And then we will talk about performance considerations. We will see how we can optimize the execution of GPU programs by taking into account certain techniques or certain optimization mechanisms that we definitely need to use if we want to get the most from the GPU accelerator. These are some two main, most important recommended readings. The first one is the CUDA programming guide. Even though it's not the only way of programming GPUs, we will also mention OpenCL over the course of the lecture. But let's say that the most successful programming language for GPU programming is CUDA. So you have the link to the GPU to the CUDA programming guide there. And if you want to read a book, there are several interesting books, but I would strongly recommend you Programming Massively Parallel Processors by Professor Hu and David Kirk, chief scientist in Nvidia. It's a very nice introduction to GPU programming. Before we start talking about the GPU programming, but we are going to very, very quickly review some slides that we were already looking at in lecture 7. You might recall this slide since year 2000. Actually, it was even before, in 2007, where the first GPUs, the G80 architecture that could be used for general purpose programming was released. There has been an exponential increase in the processor, in the performance and peak performance of the GPUs from 2009 to 2017 with the V100. As you can see in the slide, we can say that the peak bandwidth has increased by more than 15 times, right? So it's quite impressive. And this is, as you know, it's like very boosted or pushed by the recent advent of machine learning and neural networks that are exploiting these days the potential, the power of the GPUs. So this was the slide that we showed for this very first generation, this GeForce GTX 285, which only contain 240 so-called stream processors that are actually what we in the vector processing lecture call vector lanes. If you look at the most recent Nvidia V100, it's more than 5,000 of these vector lanes. So you can see how much the potential of these GPUs has improved. This is like a overview, like a block diagram of the V100, and as you can see in the slide, the V100, as any other GPU, is composed by many of these blocks that are called streaming multiprocessors in NVIDIA terminology. They are called compute units, for example, in AMD GPUs, and we can simply call them SIMD units. So if we look at them, we see that they are composed by different components, among which we can highlight the instruction cache, the warp scheduler, and the dispatch unit who read from the instruction cache and issue instructions on these execution units. We have different types of execution units, something that is typical in array processors, as we were already discussing in lecture 7. Here in this case, for example, we have specialized units for floating point, double precision floating point operations. We have single precision floating point. We have integer units, and also we have these new so-called tensor cores that are supposed to be, that are actually super optimized compute units for deep learning, because they execute like very fast matrix operations that are needed for the deep neural network training and inference. So yeah, this is, let's say, like the streaming multiprocessor. You can find more information about this Volt architecture here in this link. If we recall this pictorial representation of the streaming multiprocessor, the SIMD unit, you remember that it was something like this. You can clearly, easily recognize the same components that I have described in the previous slide. We have the instruction fetch stage and decode stage. Let's say that these two are done by the warp scheduler and the dispatch unit, and here we have the register file that is feeding operands to the ALUs, to the arithmetic logical units, and here we have access to the memory, to the data cache, and write back operation to the register file again. So as you also might also remember, the GPU implements a fine-grained multi-threading architecture. This means that we have the threads organized into something that are called warps, and a warp, as it's defined in the slide, is a set of threads that execute the same instruction. And what the warp scheduler is doing is taking one instruction for one single warp and issuing it onto the vector lanes. The fine-grained multi-threading architecture allows us to interleave the execution of instructions from different warps. And this is going to be, you might remember, very beneficial for hiding long latency operations. It's, as the slide says, fine-grained multi-threading enables long latency tolerance. You also recall this slide. How do we execute these 32 threads that belong, or the set of threads, 32 typically in NVIDIA architectures, that belong to the same warp? How do we execute them onto the hardware? It depends on how many functional units we have, right? If we have one single functional unit, we will need to execute the operations. In this case, is an addition. We will have to execute them in a pipeline manner. So we would be simultaneously running instructions, executing instructions in time. But if we have more than one of these functional units, we can take advantage not only of the pipeline, not only of the time, but also of the space, the ability to concurrently execute operations in different units and in different space. Where are the operands coming from and going to, the results going to for these ALUs or for these execution units? They are going to the registers, right? You remember this slide where we have this register file, and this register file is partitioned in a way that a certain number of registers are assigned to the different threads that we are going to execute. In this specific case, observe that, for example, in these execution units, threads with thread ID 0, 4, and 8 are going to be running. They will run in an interleaved manner, as we described before, and the registers that these threads are going to use are in this part of the register file. And it's the same for the rest of vector lanes. And how are the warps executed? Well, assuming that in this particular example we have warps of 32 threads and 8 lanes, the way that the warp scheduler will issue the instructions, the operations on the compute units will be something like this. For example, for the load unit, we will execute some load operation, or we will start some load operation for warp 0 because we have only 8 lanes but 32 threads. The way that they are going to be scheduled is in this way. So they will be scheduled in 1, 2, 3, 4 cycles. As soon as the warp scheduler issues the very first instruction, in this case this vector load, it can issue the next instruction. In this case, it's a multiply instruction for warp 1. And then one addition, and then again one load instruction, in this case for warp 3, and then we have warp 4 and warp 5. Observe that also the fact that we can have concurrent execution on the different units is also the way that we are going to hide the long latency operations. As you can guess, these accesses to memory that are started in the load unit take longer than the execution of a multiplication or an addition. So what the warp scheduler is going to do, or will try to do, as long as there are eligible warps, as long as there are warps ready for execution, warps whose operands are ready for execution, is hiding these long latency operations by running, by issuing instructions and executing instructions in the other available units. In this case, multiply and addition unit. Any questions so far? Okay, so then let's start talking about how to program GPUs. And you might also remember this slide, vector processor disadvantages. We were talking about vector processors. We said that vector processors can allow us to, exploit data parallelism that inherently exists in many applications, but they have disadvantages. And one of the main disadvantages that was pointed out by Fisher in 1983 is that it's difficult to program them. You can read this. To program a vector machine, the compiler or hand coder must make the data structures in the code fit nearly exactly the regular structure built into the hardware. That's hard to do in first place, and just as hard to change. One tweak and the low-level code has to be rewritten in a very smart and by a very smart and dedicated programmer. So already in 1983, Fisher pointed out that it was very difficult to program these vector processors, and that's actually the real evolutions in graphics processing units. The fact that they are much easier to program because they have, instead of programming them as traditional SIMD processors, vector or array processors, they can be programmed with this SPMD, single program multiple data programming model that makes our life much easier. And that's the reason why we can say that GPUs have democratized high performance computing because they are easy to program these days, or easier to program these days, and also because they put a lot of flops, a lot of gigaflops at everyone's hand, right? For very few money. Where are they going to be useful? Usually in applications that exhibit inherent parallelism, but there are many applications that exhibit inherent parallelism, especially data parallelism. We can talk about matrix operations, we can talk about image processing. These days we talk about deep neural networks. In all of them we have a huge amount of data parallelism that can be exploited by all these vector lanes, all these streaming processors that we have in current GPUs. This is not that easy, obviously, because we need to learn how to program them, but it's not that difficult, as you will see. And we will still have some bottlenecks. Obviously, there's no free lunch, right? And the bottlenecks, as I already mentioned, and as also you can expect, are actually in the data access, in the data movement. So because this is like the main problem in most of computing systems these days. And we have two bottlenecks related to data movement in GPUs, at least in discrete GPUs, which are like the most widely used. The first thing is the data transfers between CPU and GPU, because it's in CPU where the programs start executing, and it's in the main memory of the CPU where we are going to originally have the operands, the input data, and we need to transfer this input data to the GPU so that the GPU can start operating on them. The way that we are going to do that is typically using the PCI Express bus. Recently, like 2-3 years ago, Nvidia, in collaboration with some partners, for example IBM, launched this NVLink that is faster, let's say. So the problem is still there, but it is true that NVLink can provide higher bandwidth than PCIe. And then the second bottleneck is, as you could expect, the access to DRAM. Even though, well, since the very beginning of the GPU computing era, or the GPGPU era, the memory bandwidth has increased a lot, but still it's a bottleneck. Most recent GPUs use GDDR5 or GDDR6, or even HBM2, that is 2.5D stack memory. So, well, this is very, very briefly to recall what are the main differences between CPUs and GPUs. And you can, as you can see, the main difference is where are we spending the die area, right? The chip area. In the CPU, we spend a lot of area on control, branch predictors, speculative execution, etc., and having large on-chip caches. In the GPUs, we have in-order cores, so we don't need so much area for them. We have very small caches typically, and what we have is a lot of cores, right? A lot of SIMD lanes. Okay, and yeah, let's start with what we call the accelerator model. We say that in this accelerator model, we consider the GPU as an accelerator, or a coprocessor, typically a loosely coupled coprocessor or accelerator. And in summary, there are like 3 steps when we want to use a GPU, and these 3 steps are kind of obvious, right? The first one is the data transfer from the CPU to the GPU, because we have the input arrays, the input data into the CPU memory, and we want to transfer it to the GPU for the GPU to operate on it. Then we have the kernel execution. When we talk about kernel, what we mean is the function that is executed on the GPU hardware. And the third step is the data transfer from the GPU to the CPU, because we want to transfer, to move the results that the kernel has produced from the GPU memory to the CPU memory. And the program, the way that it's going to be organized is something like this. We will have sequential or modestly parallel parts of the code executing on CPU, and massively parallel sections executing on the GPU. So it's the way that, let's say, we organize a traditional heterogeneous computing programs, something like this. You can already observe how the computation is organized on the GPU. This is the collection of threads that are going to execute this parallel kernel that runs on the GPU or device. From now on, we will use interchangeably GPU and device, as same as we will use interchangeably CPU and host. So now we talk about host and device, CPU and GPU. And the way that we invoke the kernel, the function that executes on the GPU, is by using this command or this instruction here. This would be kernel B, or kernel A would be is the name of the kernel. And as you can see in this part, what we have is what we call the execution configuration. The execution configuration is composed initially by two parameters that are the number of blocks and the number of threads. And what are they? Well, you can guess that the threads are all these little guys that are here that are going to be assigned to some specific instance of the input data and are going to run some particular code. But these threads, from the programming point of view, are going to be organized into blocks. So here you can see several blocks that belong to the same grid. Okay, so we talk about a grid composed by blocks, composed by threads. So we specify how many blocks and how many threads we want to launch for this kernel, and we have here the arguments of the kernel. You already recall, pretty sure that you recall this slide about the single procedure or single program, multiple data programming model. As the slide says, is not a computer organization, it's a programming model. The computer organization, in this case the GPU organization, is still very similar to a vector or an array processor in the way that we have already studied them in the course. Now the novelty is that the way that we are going to program them is much more, let's say, flexible, much more programmer friendly. And from that point of view, it's also going to be much more productive, right? The main thing in this single program multiple data is that we have multiple instruction streams that execute the same program. And these instruction streams is what we have just called threads. And we will use the term threads throughout the rest of the lecture. So this SPMD, also called SIMT, Single Instruction Multiple Thread Programming Model, is a bulk synchronous programming model. And what does it mean? This means that if we want to synchronize these multiple streams of instructions, these multiple threads that are going to run in parallel or concurrently onto the GPU hardware, we will need to terminate the kernel. We will need to recall that kernels are the functions that are launched onto the GPU. So if we want to make sure that these guys reach some point and they stop and wait for others to finish, the only way to do that is terminating the kernel. So this is why it is called bulk synchronous, right? Because we are synchronizing all the threads at the same time, and this requires terminating the kernel, and then if we want to continue the execution, we will have to relaunch a new kernel. This has inherently some drawback, right? The fact that launching a kernel from the CPU to the GPU requires some time, requires the driver to do it, and this entails some overhead that will be, depending on the kernel, actually, depending on the computation that we're going to do on the GPU, will be an overhead or a burden for the entire performance. But still, we will probably get a lot of benefit from using the GPU. So what the host, the CPU, is going to do? It will allocate memory on both, obviously, the memory of the CPU and the device memory or the global memory of the GPU. Then we will need to move the data to copy it from the main memory to the device memory or the global memory, and then launch the kernel. And what the GPU is going to do? The important part, right? It's executing the kernel. I have already mentioned these three terms: grid, block, thread. The reason why these threads are organized within the blocks, I mean, there are, let's say, I could say two main reasons. The first reason is that the GPU itself is divided into so-called, in NVIDIA terminology, SMs, or streaming multiprocessors, that are each of these compute units or SIMD units that we have already seen in the previous slides. So if we want to launch the kernel, the kernel and launch the threads to execute, to run on the vector lanes, we need to somehow group these threads and put each of these groups or blocks of threads into each of these SIMD pipelines or SIMD cores. That's one reason, to organize the threads into blocks. And the second reason is the possibility of sharing data across these threads that are going to run in the same compute unit or in the same SM, and also synchronize them. Observe that we just said it wasn't possible to synchronize threads unless we terminate the kernel, but actually this is when we talk about a global synchronization for all the threads of the GPU. But at a block level, within each of the compute units, within each of the SIMD units, it's possible to synchronize the threads that belong to the same block. So, related to the first reason that I mentioned, the fact that we are going to launch a kernel grid composed by a certain number of blocks that we define in the execution configuration, and we need to assign these blocks to the compute units, right? To the SIMD units, and start the execution. But it turns out, and as you know, that the number of cores, the number of units that we will have in each GPU will depend on how much we pay usually, right? So if we have a mobile GPU as the same as we can have on a mobile phone or a laptop, probably the number of these SIMD units that we will have will be something between 1, 2, and maybe 10 of these units. But if we have a high-end GPU, one like, for example, these Volta V100 that are used to train neural networks, we will probably have up to 80 of these units. But still, when the programmer writes the code, we just want the programmer to write the code once, right? So organizing the threads into blocks allows us to take advantage of what is called the transparent scalability. Depending on how many cores do we have, maybe 2 or maybe more, we will launch the kernel over time, taking advantage or using the available compute units. Here, for example, we have 2, here we have 4. The way that we are going to schedule these 8 blocks is in this way for the 2-core device, block 0 and block 1, then block 2 and block 3, and so on. Here we can schedule 4 blocks at the same time. Still, there is no guarantee that the blocks are going to be executed in order. Observe that here the blocks are numbered. Each of the blocks has an index. And in principle, we can think, oh, probably block 0 is going to execute before block 1 or block 1 before block 2. There is no guarantee of that. So the hardware doesn't give us any guarantee of the way that the blocks are going to be executed on the SIMD cores. Okay. Now, how is the memory hierarchy organized? It's as you can, well, as we are going to see, it's different from the memory hierarchy on CPUs. In CPUs, you are already familiar with them. We have the main memory, and then we have several, maybe 2, 3 cache levels. Here, we also have cache. We have actually 2 cache levels, but there are more levels of, let's say, memory, on-chip memory, that can be used by the threads. This is somehow an abstract view of the memories. Let's say that this is like the programmer view of the memory hierarchy, because you cannot see caches here, right? Why is that? Because caches are handled by the hardware transparently to the programmer. So the programmer has no idea if something is cached or not. But what we have in summary is one big device memory that is actually contains these 2 orange rectangles that you can have here, that you can see here. Part of this memory can be used for constant data, for read-only data. That's why some part of it, the amount that we want to allocate, by the way, is called the constant memory. This device memory can also be, it's actually also be used for graphics processing. We are not going to talk about graphics here, but that's why we can also allocate textures and surfaces in this memory. For us, all this big memory, device memory space is going to be called the global memory. That's for the GPU programmer, the way that this memory is referred to us. Observe that this memory, this device memory, can be accessed not only by the GPU threads, but also by the host through the PCI Express or NVLink, as I mentioned before. And observe that also this global memory can be accessed by all the threads that are running on the GPU, no matter which block they belong to. This would be block 00, this is block 10, for example. And as you can see, all the threads can access the global memory. But observe that the threads that belong to the same block have access to some on-chip memory that is called shared memory. It's a scratchpad memory. It's some kind of programmer managed cache. So it's the programmer who specifically says how to use this scratchpad memory. And then each of the threads have its own registers, as we already knew, because actually we recall that in a previous slide. Okay, let's start taking a look at some code. We are not going to read complete code in this lecture, but we will become familiar with function prototypes, built-in variables, and the specific commands and instructions that we need to allocate and move data. These are, so here you first see a function prototype for C. This would be like the typical C function that we execute on the host. And this is the function prototype for the kernel, for the function that we are going to execute to run on the GPU. Let's say that we start writing a program. We start writing our main function of some C or C++ program, and we want to use the GPU. So the very first thing that we will have to do after having allocated the memory that we need to allocate in main memory of the CPU, the very first thing that we will do is allocating memory on the device memory, on the global memory. And the way that we are going to do it is using not malloc, but something called CUDA malloc. how much space do we want to allocate? This number of bytes, and we need a pointer that is this D in. So this is the pointer that is pointing out to this amount of bytes that are reserved in the global memory. After that, we will need to transfer data from the host to the device. We are going to do it using this CUDA mem copy that moves some bytes from a memory address in the host to some memory location in the device. Then we decide what's going to be the execution configuration, what's the number of blocks and the number of threads that we are going to launch, and then we call the kernel. You're already familiar with this, and when the kernel terminates, we will move back or move the results from the host, from the device to the host, from this D out to this H out in main memory. We can repeat this as needed, maybe because it's an iterative algorithm and we call the same kernel many times, or maybe this simply means that we are calling a different kernel. First kernel A, then kernel B, and maybe between these two we are moving data back and forth between the device and the host memory. So so within the kernel, well, actually you already see, and you will see that CUDA is very similar to C coding. It's like kind of C with some extensions, so we can use automatic variables. These automatic variables are going to be allocated by the compiler into the registers, and then as programmers we can define how to use the shared memory, this scratchpad memory that is on chip, that is within each of the compute units. And we already talked about the fact that we could synchronize threads that belong to the same blocks. The way that we are going to synchronize this thread is writing in our code something like these sync threads that you can see in the slide. Okay, you can find in this slide more, like the specific syntax of all these instructions. We have CUDA malloc, we have main copy, we have the kernel launch. Same as we have the CUDA malloc, we need a CUDA free when we want to deallocate memory. And the very last thing here is this explicit synchronization command, CUDA device synchronize, that is used to explicitly know when one kernel has terminated. And why is that? Why do we need that? Maybe we don't really need to use it always, but the thing is that every time that we launch one kernel, we launch one function to execute on the GPU side, the CPU gets released. Let's say the kernel launch is asynchronous, so as soon as the CPU thread launches the kernel, the CPU is free, the CPU thread is free, and can start doing another stuff, different things, while the GPU code is running on the GPU. But at some point, the CPU thread might need to know, to confirm that the GPU has terminated the execution of the previous kernel, maybe because we want to launch a new kernel, or maybe because we want to get some data, or any other reason. And this is the way to synchronize, to confirm that the kernel has actually finished. Okay, now we are going to start talking about how to organize the computation within each kernel. How are we going to write the GPU code? So observe that, and actually these concepts that we are going to cover in this part of the lecture are not so much specific to GPU programming, even though we are obviously going to use like the CUDA terminology, but they are more like parallel programming in general, how to access data when we have multiple concurrent threads and we have data structure with multiple data instances that we need to operate on. As a running example, what we are going to use are this image processing, at least in this first part of the lecture. Images, as I said in the beginning, are very interesting because they have a lot of pixels, they have many elements that we can typically operate in parallel, so they are massively parallel data structures, so that's why they are good for a massively parallel device like the GPU. And they are also interesting because they are two-dimensional, and that's why we could also use some, for example, volumes that are three-dimensional. It could be even more interesting, but two-dimensional, it's enough to understand the way that the data structures are going to be mapped into memory, and also understand the way that different threads are going to access the, in this case, the image pixels. So we consider one image with a certain height and a certain width. In this case, it's this image is a square. It's 8 times 8. And you know that if we want to access one of these pixels, the way that we are going to access is indicating what's the row and what's the column that we want to read, what's the specific location where the pixel is in the image. In this case, we have J is the row, I is the column, so J is something between 0 and the height of the image, and I is something between 0 and the width of the image. So that one, that pixel could be image 0, 1, this pixel is image 1, 2. And how are these images laid out in memory? In CUDA, same as in C, we use row major layout. So the way that the image, in this case, this image is stored into memory is linearly, right? Same as column wise, or row wise, or in row major layout, something like this. So the thing is that every time we want to read or access this image Ji, what we are actually doing is accessing element J times width plus I. So this width, we are going to call it width, but we will also talk about stride later, depending on how we access the image or how we access the two-dimensional data structure. This image 0, 1 is actually, so it's actually image 1, right? Because the row is 0, and this other guy, this image 1, 2, is actually this image 10, right? So it's a 10th element in the linear array that we have stored in memory. So how are we going to access these pixels when we launch a kernel and we have a bunch of GPU threads accessing these pixels? In principle, we are going to consider that we are going to do the same operation on every pixel, and the simplest way is assigning one of these pixels to one thread. So that's how we start. That's how we are going to start with the discussion of this. And now we are also going to consider that we use one grid that is going to be one-dimensional. So even though we are operating on a two-dimensional data structure, the threads that we are going to be using are arranged in a linear way, in a one-dimensional way. In order to identify what are the threads and the blocks, recall that the programmer organizes the threads into blocks, and we are going to have a total number of blocks. In order to be able to identify the specific threads that we want to use, we need to use some built-in variables. And these built-in variables are for the index, but also for the dimension. Observe that this is the block index, is block index.x, and this is the thread index.x, because it's only x because we are using a one-dimensional array. So all threads are organizing one single dimension for the number of threads that we have in each block is going to be defined by this built-in variable block dim.x, and the total number of blocks is this grid dim.x. So if we have one image, and as I said, we are going to assign one thread per pixel or one pixel per thread, what we will do is assigning all these pixels here to the threads that belong to different blocks. So for example, the threads belonging to block 0 are going to be working with these pixels here. The rest of blocks are going to be working with the rest of pixels. And if we go in detail to this block 0, we have it here. What we do is assigning thread 0, 1, 2, 3 to these 4 consecutive pixels. As you can see, this is just a toy example. We will typically don't have as low as 4 threads per block. We will typically have some multiple of 32, because 32 is the warp size, as you might recall. So usually our blocks will be of 32, 64, 128 threads or something like that. Here for an easier explanation, we are just using 4 threads. So we have our block index, we have our thread index. When we write the CUDA code, we need to tell each of the threads, hey, you have to access this pixel, and the way that we are going to do it is using this block index, block dimension, and thread index. So, for example, the thread that is going to operate on this pixel is the thread is thread 1 in block 6. So it's accessing pixel number 25. So if we could, this is also a way of calculating, like let's say the global thread index. The global thread index for the thread that is going to be operating on this pixel is 25. For two-dimensional blocks, we do exactly the same thing, but now instead of having, let's say, one single variable for the dimension and for the index, now we have 2. We have the grid dimension in the x direction and in the y direction. So in this particular case, we have 4 times 4 blocks, right? And here also not only the grid, but also the blocks are 2-dimensional. If we look at this thread block here, the thread block that is going to operate on these 4 pixels, this would be thread block 2, 1, right? X equal to y equal 1. And this is thread 1, 0. So now the way that we access the image pixels, if we are using 2-dimensional blocks, it's calculating the row and calculating the column using the indices in the y direction and the indices in the x direction. So for example, this pixel here, that is pixel 3, 1 in row 3 and column 1 is accessed by the thread, is accessed by thread with thread index equal 1, thread index y equal 1, and this thread 1, 1 is in block 0, block index x is 0, block index y is 1. So it's thread 1, 1 in block 0, 1. Okay, any questions so far? I don't think so, right? Okay, sounds good. So yeah, let's continue. Let's continue with more details about the GPU programming. Just very briefly review about the GPU architecture. This is one streaming multiprocessor, one of these SIMD units that are within the GPU. They are arranged in the way that you see in the slide. They are arranged in something that are called the TPCs, threads, texture processing clusters that contain some texture L1 cache that is used for graphics processing. As I said, we are not going to talk about that today. And these TPCs are organized into an array or streaming processor array. That is all this collection of TPCs containing the SMs. And that was for the original Tesla G80 architecture. More recent architecture is Nvidia Fermi. Here, as you can see, there are more compute units. Instead of having 8 vector lanes that we had in the previous generation, in this generation we have 32. And actually the interesting thing here is that these 32 cores, or vector lanes that can execute either integer operations or single precision floating point operations, are arranged into 2 groups of 16 lanes. And why is that? Because the warp that are like the 32 threads that execute in lockstep, that execute at the same time, are mapped onto this 16 or this 16. Observe that there are 2 warp schedulers, so in this architecture we can be reading 2 instructions from the instruction cache, and the warp scheduler would be launching or issuing 2 instructions for probably 2 different warps on these 16 or these 16 lanes. Where are the warps coming from? The warps, let's say, is like a hardware or a software hardware concept, because it's the way that we map the threads. Is a SIMD unit, right? That we use to map the threads onto the vector lanes, but actually where the warps are coming from is from the blocks. As programmers, we define a certain size for the block. I said before 16 or 32 or 128, and what the streaming multiprocessor is going to do is decomposing each of these blocks into multiple warps and then start executing the instructions for each of these warps. Okay, yeah, so here a little bit of terminology that we have already described or discussed previously, and here you just can see some numbers to compare what's the number of SIMD pipelines and the number of vector lanes in each of the generations of NVIDIA GPUs. Okay, so let's say that we have covered like the we have covered like the very initial and basic concepts of the GPU programming, and now we are going to continue talking about performance considerations. So, what are we going to cover in these performance considerations? Well, it's obviously related to how to overcome the main bottlenecks that we are going to find when programming and when computing on GPUs. I already mentioned in the beginning of the lecture, this is going to be the data movement, the data access, and there are 2 main things here to consider. One of them is the access to the device memory. The other one is how we move the data from the CPU to the GPU, right? So these are the 2 things that we are going to at least start describing or start discussing how we can optimize and how we can try to minimize the bottleneck that they represent. So first of all, for the memory access, we need to talk about latency hiding. Recall that the fine-grained multi-threading architecture of the GPU allows us to launch instructions from different warps, and this is the way that we are going to hide long latency operations. But in order for it to happen, we will need to allocate enough number of warps. We will need to make sure that the characteristics of our program, or the way that the program is executed, fulfill some requirements to actually be able to do this latency hiding. Related to that is also the way that we access memory. We will talk about what's memory coalescing, because as you will see, it's not, even though the SPMD programming model allows us to, let's say, write code that is going to be independently run by any single thread, we need to try to do it in a smart way, based on the knowledge that we have of the architecture, and this also means how are we going to access. So that's why we will talk about how to write the code in a way that we do coalesced memory accesses that are going to be the most efficient way of accessing the global memory. And then, because in some cases or in many computations we will have data reuse. This data reuse, as you know, is typically exploited by caches, but because the caches are not that large here in the GPU, we should also learn how to use this scratchpad memory, this shared memory that is some kind of programmer managed cache. Another thing that we are going to discuss is about divergence. This is already something that we discussed in the vector processing lecture, and actually you even had a related question in the midterm exam, right, about SIMD utilization. We are going to talk about this, and we will put one or two examples about how to change the code structure to have a more efficient execution that increases the SIMD utilization. We will also talk about an important class of operations that are atomic operations that are very, very useful for example, thread synchronization, but they are very good, let's say, in terms of programmability, but they have an important drawback, that is the fact that the access to memory is going to be serialized. We will see also one technique for how to deal with this in one specific type of application. And finally, we will see what we can do with the data transfers, because there's a possibility of overlapping data transfers with computation. If we divide, let's say, the bulk thing that we need to operate on into different parts, we can start the computation on one of these parts while we are while we are transferring data for the second part through the PCI Express bus. So let's start with the memory access, and let's recall what's the latency hiding that we can achieve using the fine-grained multi-threading architecture. To do that, we need to ensure that the occupancy is high enough. At least this is the very first way of doing this, of doing that. And what's the occupancy? Well, the occupancy is defined as the ratio of active warps to the maximum number of warps that we can have on one of the SIMD pipelines or one of these GPU cores. As you can guess, we cannot, or the hardware cannot map as many warps as we want, right? There will be some limitation. Can you guess how is, where is this limitation actually? Where can we have this limitation? Well, there are two main things. One of them is the program counter. We will have some limited number of program counters in each of the GPU cores, right? And the other one is the mask. As you know, in these GPUs, same as in vector processors, we use mask operations, and the number of available masks is also limited, right? So it's actually going to be the same as the number of program counters or instruction pointers that we have in each of the cores. So there is a maximum of warps that can run on the same GPU core, and depending on the characteristics of our program, we will achieve this maximum or not. And the value, the ratio of active warps that we are actually going to have is what we call the occupancy. And observe how this is like a very, very naive toy example of what can happen if we have, let's say, 4 active warps, or we have 2 active warps. In case that we have 4 active warps, observe that here over time we start executing instruction, or we are executing instructions. This is instruction 3 for warp 0, then instruction 2 for warp 1, and then instruction 4 is a long latency operation, maybe a memory access for warp 0. So it's going to take longer. What can we do in the meantime? Because this is going to use the load unit and then go to the memory controller and access to memory. And in the meantime, the way that we can hide this long latency operation is by issuing instructions that belong to different warps, right? It's a very simple example here, but at least should be good to illustrate how we overlap the execution on arithmetic units with the execution of memory accesses. And here, if we only have 2 warps, what will happen is something like this. At some point, there won't be more eligible warps. There won't be more warps whose operands are ready so that they can be taken by the warp scheduler and the instructions issued on the onto the vector lanes. So as you can see, we will have to wait, we will have all this gap until the long latency instruction finished. The occupancy is determined by the amount of resources that we are going to use. First of all, I already mentioned that we will have a maximum number of warps that can be running on each of the GPU cores. And this number is determined by the number of program counters that we have there. But there are also other resources that might exhaust. For example, there is also a maximum for the number of blocks that can run in each SM. In the slide where we talk about the transparent scalability, you saw that each of the blocks was mapped onto a core. Actually, in each of the cores, we can have more than one block, and each of these blocks is decomposed into warps, and these warps are scheduled independently. And then we have some number of registers, and we have a certain size of the shared memory. And these registers and this shared memory are going to be distributed across the running warps and across the running thread blocks, right? So, I don't know, let's say that in a current architecture, the size of the shared memory is 64 kilobytes. Let's say that one programmer, for whatever reason, decides that for each warp, for each block, sorry, he needs or she needs 32 kilobytes. How many blocks can we schedule on each of the cores? We can schedule 2, right? So it will be a pity if for some reason the programmer decides that we need 33 kilobytes for each block, right? Because the problem is that we will only be able to schedule one single thread block in each of the cores, and we will be wasting 31 kilobytes of shared memory. So that's why it's important to try as much as possible to make a good use of these resources. This is the way we can calculate the occupancy, taking into account what's the usage of these resources. Okay, I think this is a good time to stop. What if we have a, let's say, 10-minute break? Right now it's 1:20. Let's continue at 1:30. Any questions so far? No? Sven? Joe? No? Okay, thank you. Let's continue in 10 minutes. So, yeah, we're going to continue with we were with the performance considerations. Now we continue with the memory coalescing. How are we going to access the global memory of the GPU in order to take the most of it, to have the highest, to get the highest possible bandwidth? And the key here is to do what are called coalesced memory accesses. And this essentially means that concurrently running threads, that is those threads that belong to the same warp, are going to access nearby memory locations. So the peak bandwidth utilization occurs when all the threads in a warp access one cache line. This is something that probably you could be guessing already, right? Because we access memory on a cache line granularity. So if for some reason we need, and we have the threads of the same warp executing in lockstep, right? Being launched and running at the same time. So it makes sense that if we want to get the maximum bandwidth, these threads access the cache line. By the way, unlike typical CPU or traditional CPU architectures where you will usually find that the cache line size is 64 bytes, in GPUs it's typically 128 bytes. And why is that? Because integers and floating and single precision floating point operands are 4 bytes. We have 32 threads in the warp, so 32 times 4 is 128 bytes. And here you can see like the very first two examples of what a coalesced or an uncoalesced or not coalesced access is. Here we have two matrices, MD and ND. And these orange lines are, let's say, highlighting the way that threads are going to access throughout the data or the elements of these two matrices. So for example, here in this case, we have two threads, thread 1 and thread 2, they belong to the same warp block and to the same warp. And the way that the programmer has written the code makes that these threads access the matrix in this way. So they start going over one row. You see, thread 1 accesses this row, thread 2 accesses this row. What's the problem here? The problem is that these two threads execute concurrently, right? They belong to the same warp, they execute in lockstep. So in the very first iteration, they will be accessing thread 1 here and thread 2 here. And observe that if these two guys access or want to access the matrix at the same time, they are doing it with some stride, because this thread 1 accesses here, thread 2 accesses here, and the distance between these two is the stride that is equal to the width of the matrix or the image in this case. The problem is that unless this width or this stride is very, very small, let's say this matrix is 2 by 2 or something like that, these two threads will be probably requesting the access to memory elements, to matrix elements that are going to reside in different cache lines. Problem, we will need two memory accesses, right? One for the first cache line, second one for the second cache line. If we are smart enough, we can write the code in a way that the threads are going to access this way. So if we have thread 1 here and thread 2 here, observe that these two are accessing consecutive columns. So the elements that belong to, consecutive elements that belong to the two consecutive columns are going to reside in the same cache line. Here you can see probably a more clear example. In the uncoalesced memory accesses, we have threads accessing by rows of this matrix, because the matrix it's actually lies in memory in this linear way in a row major layout. If we have thread 1, 2, 3, and 4 accessing the first element of each row, and also depending on what's the stride, depending on what's the width of the matrix, probably these threads 1, 2, 3, 4 will be accessing different cache lines. So problem here is that we will need 4 memory requests to access the very first element of each row. This is for the, let's say, the first iteration, the access to the first element, or first time period. For the second time period, we might need to access again 4 different cache lines. So this will also depend on our caches, right? On our cache hierarchy and what's the size of this cache hierarchy and of these caches, and how much we can of the cache line we can keep in the on-chip caches. In a coalesced memory access, the direction which we are going to access is like this, so threads accessed by column, and the good thing is that in the first iteration or first time period we will have threads 1 to 4 accessing 4 consecutive elements of the matrix that probably will belong to the same cache line, so in one single memory request we can fetch all the data that is needed by these 4 threads. Then this would be for time period 2, etc. So this distinction between the coalesced and the uncoalesced memory accesses is not only related to the way that the programmer writes the code, but it's also related, and probably more importantly, related to the way that the data structure is organized. And observe that if we are using, for example, here we are talking about matrices, about images, which are two-dimensional organizations, and one way of representing this dimensional or multi-dimensional organization is by using structures, right? So for example, here you have 2 different structures. The first one is called the structure of arrays. So we are using one structure, and each of the elements of this struct is one array of 8 elements. Here we have float A8, float B8, and so on. Here, on the other hand, what we have is this array of structures. So it's an array called A of size 8, and each of the elements of A is one of these float or integers that we have there, right? So the way that this structure of array or this array of structures are going to look like in memory is something like this. In the structure of arrays, we have all the blue A elements together, and then we have all the green elements, and then we have all the yellow elements, and so on. Here what we have is for each of the structs, we have blue, green, yellow, and so on together, right? Okay, so what's going to be the difference between these two in terms of performance? It's going to depend on how we operate on this data, right? But observe that typically we are going to use many threads on the GPU, right? And when we use many threads on the GPU, we organize these threads in blocks, and these blocks are decomposed into warps. And these warps are a collection of 32 threads that execute in parallel, execute at the same time. So, and they are also executing the same code, right? And we do it this way because GPUs are good for data label parallelism. So if they are executing at the same time and they are executing the same code, it's very likely that the very first thing that they do is accessing the blue elements. And probably we will have thread 0 of the warp reading this blue element, thread 1 reading this blue element, thread 2 reading this blue element. And when they finish with the blue elements, they will go to the green elements, and we will access this one and this one and this one by 3, 4, 32 consecutive threads. So if we do it this way, the good thing is that for the very first access, we will be reading float elements that belong to the same cache line. So we will have a coalesced memory access. However, if we use an organization like this, we will need to have thread 0 here, thread 1 here, thread 2 here, and so on. There will be an stride, a distance between the accesses of the consecutive threads. So probably we will be accessing more than one cache line, thus reducing the coalescing opportunities and having worse or lower exploitation of the available bandwidth. Is that clear? However, observe that even though the preferred one for GPUs is this one, which by the way is the same as directly using discrete arrays, we don't need to arrange the arrays in a struct. They could be directly declared and allocated as discrete arrays. This is good for GPUs, but observe that this is going to be good for CPUs. For example, let's consider that these blue, green, red are like the different channels of a pixel in image processing. So if we have a CPU operating on an image, operating on a color image with 3-4 channels, what we will need is that the CPU thread operates on one pixel and then goes to the next pixel and then goes to the next pixel. And it's probable that when we operate on the first pixel, we operate on the first pixel, we need to access the red, green, and blue channels, right? So for a CPU, it's good that if the first thing that we access is the green value, the consecutive elements are the other channels. In the case of the image pixel, they belong to the same cache line, so that when we read the blue thing, we are also bringing the green, the yellow, and the red thing to the cache. And in the next access to memory, the CPU thread will find the next color or the next channel in the cache. So that's why the throughput for CPU and for GPU might be different and might look like something like this. So here, these are experiments run on an AMD Kaveri. AMD Kaveri is a CPU, GPU integrated system in the same chip. We have a CPU and we have a GPU. If we access the same data structure with a specific structure size, with a specific stride across consecutive accesses, you will see that the throughput for the GPU goes down very quickly when we increase the stride. However, the trend, it's somehow different for a different number of CPU threads, of different number of CPU cores in this case. So, well, you can find more details about these array layouts in that paper. Okay, so the next thing to talk about, we already know how to, let's say, be efficient in the access to the global memory, trying to organize the computation and organize the data structures in a way that we can exploit the memory coalescing, and we don't need, we minimize the total number of memory requests per warp. But now, we are going to discuss how to use the shared memory. Recall that the shared memory is this on-chip scratchpad memory that is managed by the programmer, it's explicitly managed by the programmer, and because it's on-chip, its latency, it's about 2 orders of magnitude lower than accessing the DRAM, accessing the global memory. So it's really necessary for performance to make a good use of this shared memory. However, when is it really useful? When we have data reuse, because if we are in a streaming application where we just read one element, do some computation, and store the result, and then read the next element and store some computation, so do some computation and store the result, and so on, and we never reuse these elements, it doesn't really make sense to store anything in the shared memory, right? We will use the shared memory when there is some data reuse, but it's very likely that we will find data reuse in many applications. For example, operations with matrices. In a matrix multiplication, we will have a lot of data reuse, or in some of the image processing things like convolutions, we are going to have data reuse. So learning how to use the shared memory, or discussing what are the performance considerations for the shared memory, it's actually something really very important for a GPU programmer. So let's consider again our image. It was an 8x8 image, and let's apply some filter to this image. We want to apply some kind of filter into the image because we want to, let's say, improve the image. For example, remove some noise, right? For example, we can use a Gaussian filter into smooth the image, the appearance of the image. So the way that we apply the computation with a Gaussian filter is going to be something like this. Observe that this is kind of convolution, right? We are going to use a mask that is this Gauss, we are going to apply this mask to every single pixel of the image. And the way that we apply the mask is we put it on top of the pixel that we want to operate on, and we do this multiplication between the element of the mask and the pixel that is behind it in this case, right? And we multiply and accumulate, and the final result will be this sum. Observe that actually what we are doing here is some kind of equalizing the values of the image pixels if we compare the output with the input, because in the output, each of the output pixels will have something of the surrounding pixels. In this specific case, the size of the mask is 3 times 3. And observe that the interesting thing here is that if this is a sequential code. In this sequential code, we first operate on this pixel, we later go to this pixel, then this pixel, and so on. And observe that when we move to the next pixel, actually, we will need to reuse some of the pixels that we already accessed when we wanted to compute for this one. In particular, this, and this are going to be used again when we compute the output for this pixel. So here, out of 9 pixels, we will be reusing 6 of them. And that is one specific example where using the scratchpad memory can be really interesting and can give us a lot of performance improvement. And actually, the way that in GPUs we are going to do that is by dividing the image into tiles, into different parts, and loading the images, loading these tiles that will be typically assigned to one thread block, to one block of threads, loading them into the local or shared memory, this on-chip scratchpad memory that is declared with this shared qualifier. So this is just like, half pseudocode, half CUDA code. But as you can see, we first declare the shared memory with some specific size. Then we load the tile into shared memory. We don't have the specific code here, but as you can guess, what we are going to do is assigning each of these pixels, each of these 4 times 4 pixels to one thread. The threads will go to memory, they will read from memory, from global memory, and they will store into the shared memory. Then we need to synchronize the threads, and we need to do that because we want to make sure that all the threads that are going to read this tile completely finish this operation of going to global memory and storing into shared memory. That's why we need to use these sync threads, and then we do the computation for all the different pixels, and here, instead of accessing global memory for the image, what we are accessing is the local memory or the shared memory, the scratchpad memory, where we have stored this style of the image. Okay? Yeah, so using the shared memory in a smart way is not only important for image processing, but also it's essential for linear algebra operations, matrix operations. For example, as you might know, current deep neural networks are based on convolutional neural networks, and the operation that, or the computation that we do in these convolutional neural networks is actually very, very similar to this convolution that we have just seen for this Gaussian filter. So making a good use of the shared memory, same as making a good use of the register file, it's essential to achieve the highest performance, the highest throughput, and which will translate into how fast we can train the neural networks, right? So that's why it's important to know all these concepts. Okay, so, but there are some things to keep in mind. It's the fact that the shared memory is a interleaved or banked memory, and actually that's what it should be, right? You remember when we were talking about vector processors, we also talk about interleaved memories, and we said, okay, it's for a vector processor, it's going to be very useful that we have a memory that is divided into multiple banks so that these banks can be accessed in parallel, and because essentially the GPUs are SIMD pipelines, SIMD processors, it makes sense that this shared memory is also an interleaved or banked memory. Each bank can service one address per cycle, and we can be accessing several or all the banks in parallel at the same time. In current GPU architectures or NVIDIA GPU architectures, we have 32 banks, and the way that addresses are mapped into these banks is as you could guess, same as we saw for vector processors, is using this modulo operation so that consecutive addresses are stored in consecutive banks. And it says bank conflicts. This is like like the typical thing that the programmer should keep in mind. Bank conflicts are only possible within a warp. Why is that? Because we issue the instructions per warp on a warp granularity, right? So we will have 32 threads accessing memory in parallel. The next 32 threads that belong to a different warp, they will access, let's say, one cycle or several cycles later. So there will be no possible bank conflict across warps, but the bank conflicts can only happen within a warp. And this is a very, pictorial representation on what a bank conflict-free access pattern is. Here we are considering, in this case, only 16 banks. We have 16 threads. Just consider that the size of the warp is 16 in this case. With a stride 1, we have thread 0 reading from or writing to bank 0, thread 1 to bank 1, and so on. Another possibility is something like this, a random addressing. Still, even though the accesses are random, still we have one bank being accessed by only one thread, so there is no bank conflict, so we can get the maximum bandwidth from the shared memory. But it will be very frequent that we have bank conflicts, and we will talk about n-way bank conflicts. What's going to be n? It's going to be the number of threads that are going to be accessing, reading or writing from the same bank, as long as they are not reading or writing to the same memory address, right? To the same memory position. Because if we have two threads, let's say, like in this example, thread 1 and thread 8, reading exactly the same data element, we just need one access to this bank, because as soon as it's read, it can be broadcast to all the threads that need this value. So this is actually efficient. This is really inefficient, or we really have a two-way bank conflict when, in this case, thread 0 and thread 8 access different elements that are in the same bank. So in this case, a stride of 2 is producing this two-way bank conflict. So observe that here also the strides are going to be important. This is also something that we mentioned in lecture 7. If the stride and the number of banks are prime relative, we won't have bank conflicts. As long as they have some factors in common, we might have bank conflicts. And here is an 8-way bank conflict as an example. Okay, so how can we reduce the bank conflicts? I think that we already mentioned this. At least we already mentioned in lecture 7 this paper for sure, so the randomly interleaved memory. This would require some improvements in the memory. Another possibility is using hash functions, as is explained in this paper. But let's say that the easiest way or the easiest thing that a programmer can do if we have strides that are not prime relative to the number of banks, what we could use is padding. It's a very simple technique that is called padding. And essentially padding, if I could use this, it would be better. Oh, cool. I can use it. Yeah, so let me give you a very simple example of what padding is. So let's say that, I don't know, let's have a very simple bank memory. We have 4 banks. And let's consider that our warps also contain 4 threads, only 4 threads. These are threads 0 to 3 accessing banks 0 to 3. So if the access is something like this, let's say that this guy is reading, this thread 0 is reading here, thread 1 reading here, and so on. We have a stride 1, there's no bank conflict, we get the maximum bandwidth from the shared memory. But what if what we have is something like this? For some reason, we need thread 0 will read here, thread 1 will read here, this element, and then we have thread 2 reading this element, and thread 3 reading this element. We have a two-way bank conflict, right? So what can we do in these cases? How do we apply this padding technique that, as you will see, is like very simple thing? Because we know that even though we have the strides, the accesses are regular because the stride is always 2. What the programmer could do is simply reserve or not using some of the memory addresses so that we avoid the bank conflicts. And in this case, what we are going to do is that we will never use this memory element. So this element here that was accessed by this element, let's call it 1, that was, no, there's actually 2, that was going to be accessed by thread 2, now is going to reside here. So when we have thread 0 reading here, thread 1 reading here, thread 2 will be accessed here, will access here, and thread 3 will access here. By just doing this, by just reserving some and not using some of the memory addresses, we can avoid the bank conflict. So we would be also doing the same for this element here, from this element here, and so on. It's clear, right? Okay. Okay. So, yeah, now we are done with memory access. We have discussed how to improve or how to optimize the access to the global memory with the coalesced memory accesses. We have talked about the data reuse. Now we are going to talk about, you know, the efficiency or the utilization of the SIMD pipelines. That's the SIMD utilization and how we can try from the programmer perspective to avoid the this divergence that is going to make threads belonging to the same warp going through different paths, and because of that the performance is going to be degraded, right? Here you recall this example from lecture 7. Here we have branch divergence because we have a branch. Some of the threads of the warp will go through path A, the other threads of the warp will go through path B, and so on. So the problem is that in the execution of these two paths, the utilization of the SIMD pipeline is limited because the mask is 0 for some of these threads here, so we won't be really using the corresponding vector lane, so we are somehow wasting the GPU resources. You remember this was implemented by using predication, by using masks, and And now we should try to, as programmers, write the code in a way that, as much as possible, we try to avoid this branch divergence or intra-warp divergence. So you have here some very simple code where we have some threads belonging to the same warp. This is one warp. We have the warp executing something, this compute function that we have here. So all the threads are active, but then we reach to this if-else statement. The even threads will go through the if, the odd threads will go through the else. We have two different paths, right? So what's going to happen is that for the if, we will have only the even threads, only half of the threads working. For the else, we will have the other half of the threads working. So we are dividing so the utilization here is 50%, right? As you already know. There might be ways of writing the code in a way that we skip that. Actually, what we are doing here is that, by the way, let's consider that instead of having one single warp, well, we have two warps. We have 64 threads running this code, right? So what we are going to do is that if we have two warps here, what we will do is remapping the computation in some way. Here you can look at the detail of the code by yourself. Remapping the computation in some way that the if path that was executed by the even threads now is going to be executed for those threads that have a thread ID that is lower than 32, and the else is executed by, instead of the odd threads, by the threads that are greater or equal to 32. This is just some synthetic code, some sample code, but here you have a practical example that actually is very useful and very important in many different applications. Is parallel reduction. Usually we will use parallel reduction when we have an array of elements and we want to obtain one single value out of these elements. For example, we want to add all these elements of the array, or we want to find what's the maximum or what's the minimum of all these elements of the array. So if we think about how we could parallelize this in the most naive way, what is called here the naive mapping, what we would do is something like this. Probably we will start operating on couples of these elements of the array. And we would assign one thread, in this case thread 0, to add or compare these two elements, 0 and 1, and then we will have thread 2 operating on these 2 and 3, and thread 4 operating on 4 and 5. And now observe that this is a reduction, so if it's a reduction, we are going to need a certain number of steps. What's the number of steps? If we have n elements, the number of steps is log n, right? And in each of the steps, the problem is that half of the threads are retiring. Half of the threads stop working. So if we go to iteration 2, now here the reduction is an summation, right? We are adding up all the elements of the array. So after having here even threads in the first iteration, in the second iteration we would be adding this thing here and this thing here and producing this result. And we only need one thread for that. So now instead of having even threads, we only have threads that are multiple of 4, right? So thread 0, 4, 8, and so on. And it's going to be worst in the next iteration, and in the very last iteration we will only have one thread. That's okay, because obviously we need one single thread to execute the last addition. But the problem with this code, what is the problem with this code? The problem with this code is that it has very low SIMD utilization, because in every iteration we are retiring half of the threads, and in the way that we have written the code, the threads that are retiring are those, or so that the threads that are not retiring, the threads that continue executing, that are those that are whose thread ID is a multiple of the stride that we are using, and the rest of threads that belong to the same warp are going to stay idle. So problem, we are reducing the SIMD utilization in every of these iterations. So here, every time that we increase the stride, every time that we double the stride, we are, half of the threads of the warp are retiring, getting idle, and they won't execute more. So problem, low SIMD utilization in every single iteration. A lot of the compute units, or vector lanes, are getting unused. What can we do? Remapping the computation in a way that the threads that are active are always consecutive. Why is this possible? Why is this possible? Well, in this particular case, it's possible because we are executing an addition for this vector reduction. There is no, so we have the commutative law, right? So we can operate on these elements that we are using in the order that we want, and the result won't change. So that's why we could start doing something like this. We have thread 0 in the first iteration adds element 0 and element 16. Thread 1 adds element 1 and element 17, and so on. And in the second iteration, half of the threads retire, but if we have hundreds of elements or thousands of elements that we are going to reduce, the good thing is that in these initial iterations, all these threads that are consecutive belong to the same warp. So we will have 100% utilization for those warps that are really working. And for the warps that are not working because they retire, as here or here, what happens? Happens nothing. They are simply not scheduled, and that's all, right? So we are not really wasting the resources. We are just using the available resources for those threads, or those warps that are really active. So we continue, and the good thing is that instead of scheduling many different warps that are only really using part of the vector lanes, we are scheduling a lower number of warps, but they take full advantage of all the vector lanes. This is the corresponding code. It's a little bit maybe more difficult to reason, but in the end it's not that difficult at all, and we will get a lot of performance improvement from that. Okay, so this is one example of how to deal with branch divergence, how to deal with intra-warp divergence. Now let's talk about atomic operations. As I mentioned in the beginning, atomic operations can be very useful from the programmer point of view. For one reason is because they are, very intuitive, right? We have two threads, and these two threads, for some reason, want to update the same value in the output, the same element in the output. How can we do it if we don't want to have data race conditions? We need to use an atomic operation so that we ensure that the first thread goes to the value, reads it, updates and writes, and then the second one goes, reads, updates and writes. We need some support for locking the access to locking and unlocking the access to the data elements, and as long as we have that, everything will work well, and it will be easy for the programmer, or easier for the programmer. Atomic operations can be useful for computation when we have we want to have several or many threads updating the same values in the output, but they are especially useful for synchronization when we have some threads doing some computation, other threads doing some other computation, and for example we implement some producer-consumer approach where the output that is being produced by these threads here is going to be used by these other threads here. So we need some way of connecting or communicating from these guys here to these other guys here, that the output or the intermediate result is already done. You can start with the corresponding computation. If we don't use atomic operations, what we will need to use is terminate the kernel, because this is the only way of making sure that we synchronize all the threads, unless we are operating on the same thread block. In the same thread block, as you remember, we have like these local barriers for thread block. For synchronization of the threads that are in the same thread block. But if the threads producer and consumers belong to different thread blocks, we can either terminate the kernel or use atomic operations. So just as an introduction to atomic operations and how we can optimize their use, we are going to focus on shared memory atomic operations, and we are going to focus on a specific algorithm that is very useful, especially in image processing, that is histogram calculation. Atomic operations are like the one of the interesting features that have evolved over the last 10 years since the GPU, or even 12 years since the GPU computing era started. They were like very basic and highly unoptimized hardware in the very initial generations. They have improved a lot over the course of these 12 years. But still, even though they have improved, we still need some sort of serialization. So these techniques, or this simple technique that we are going to explain next, can still be useful. This is an atomic addition in CUDA. Here you have the syntax of this means that we are atomically updating this address, the element in this address, by adding this value here, and the atomic addition, if we need it, will return some, in this case, integer that is the old value. So before updating the corresponding memory location. You might know that CUDA uses some intermediate representation that is called PTX. This is some kind of intermediate language and the way that atomic operations are represented in this PTX is something like this. It's an atomic operation on shared memory, it's an addition, and it's operating on integer of 32 bits and sign integer. This is the output value, this is the memory address, and this is the value that we are going to add to this memory location. And then we have the real machine code, the real assembly code that is called SAS, and it looks different depending on the generation. This is the ISA, right? So this like the sequence of operations that we needed to use, or we need to use, is if we use one old GPU. The most recent one is this Kepler architecture that was launched in 2012. And since the Maxwell architecture in 2014, what we have is just one single instruction, because we have native atomic operations, at least for some of the atomic operations. In the old times, observe that this is actually interesting. If you read this code, this sequence of 4 instructions, what we have here is a load and lock instruction. So with this instruction, we go to memory, read from memory, and lock the access to memory. It will be only one single thread that will get the lock, let's say. And the load instruction produces one predicate register. This P0 will be 0 or 1 depending on how lucky the thread was, right? If the thread manages to lock the access to this specific shared memory position, the corresponding predicate register will be 1, otherwise it will be 0, and depending on the value of the predicate register, it will execute the addition and the store and unlock operation. And you see that also the store and unlock operation generates a second predicate register, and depending on the value of the predicate register, the thread will jump to the beginning of this 4 instruction sequence. Much more efficient in newer architectures. So, but still, in both cases, there are atomic conflicts that might happen, and we can define, a conflict degree. Same as we were talking about bank conflicts before. Now we could talk about atomic conflicts. The problem is that, in this case, for example, we have two threads, thread 0 and 1. They are updating different memory positions in shared memory. Then everything goes well because they can do it at the same time, and we will have some T-based latency. That will be the number of cycles needed to update these two elements, 0 and 2. But in case that the two threads 0 and 1 want to update the same element, in this case element 2, we will have some base latency plus some overhead, right? Some additional latency that goes on top of it. So if there is no conflict, we have concurrent updates. If there is conflict, we have serialized updates. And now, is this going to be frequent? Yes, this is going to be very frequent, depending on the computation that we do or the type of synchronization that we want to do across threads. But in the example that we are going to use today, histogram calculation, you will see that it's something that might be very frequent. This is the very simple sequential code to execute, to calculate a histogram. But if we have a parallel execution, if we have an execution, we want to generate the histogram on the GPU, we will need to have many threads running in parallel, accessing pixels belonging to the image, to the input data in this case. This thread 0 reads this element, thread 1 reads this element, and so on. And depending on what's the value of the data, it will update, in this case, will add 1 to the specific bin. In this particular picture, you see that thread 0 and thread 2 need to update the same histogram bin 1. So they will produce an atomic conflict. We need to use atomic operations here for sure, and these conflicts are going to be really very frequent in image processing. For example, when we generate, when we want to calculate the histogram of natural images, real images, observe that if you look at this tile of pixels from the forehead of this woman, we see that, because life is like that, right? So consecutive pixels tend to have very similar values. So in all this gray area, all the pixels have very, very similar value. And if we are going to be reading all these pixels in parallel by many threads running in parallel, it will happen that many times or sometimes we will have conflicts. As for example, these two threads are reading pixels with exactly the same value. So if they are going to update the histogram, they will both update bin 192, and this will produce a atomic conflict. So what can we do? What we can do is applying one technique that is called privatization. In this case, because histograms also use addition, same as we already mentioned in the vector reduction operations, because it's an addition. The order in which the additions are executed is not important for the final result. So what we are going to do is that we divide the entire image into tiles, and each of the tiles is assigned to one thread block in this case, and each of the thread blocks is going to have its own subhistogram. So instead of having one single output histogram that will probably reside in global memory and have all the threads of the GPU updating the bins in this histogram in global memory, that first of all, it's very long latency because we have to go back and forth to the main memory, to the global memory, and second, the probability of conflict is much higher, right? Because we have many more threads accessing a certain number, a limited number of memory positions, typically 256 in image processing. Instead of having that, what we can have is these subhistograms in shared memory, so that the threads go all over the image. And actually here, as you can see, the number of thread blocks that we are using is smaller than the total number of tiles, because you can see that block 0 is here, and then here, and then here, and then here. and every time that the threads in block 0 read the pixels, they update the corresponding subhistogram, and when all the subhistograms are done, then they are merged into a final histogram in global memory. So this technique is called privatization, and it, as you can guess, improves the performance of this type of operations a lot. Okay, so now we have already talked about shared memory, we have talked about atomic operations in shared memory. Now let's talk about what to do with data transfers. Recall that in the beginning I said that there are like two very big bottlenecks in GPU processing. One of them is the access to the DRAM memory. The other one is the data transfer between CPU and GPU. By the way, this bottleneck actually only exists on discrete GPUs, right? And we saw some results for the AMD Kaveri, that is an integrated system that has CPU and GPU on the same chip, so they access the same main memory. So there is no need of moving data back and forth. And this is related to the next part, the second part of the lecture that we at least will start introducing. But in discrete GPUs that actually are the most common, and these days are, as I have said before, very useful for training machine learning, deep neural networks, these data transfers are unavoidable. And what can we do? Well, the problem is that usually when we write a program for GPU execution, we will in principle use these synchronous memory transfers. And this means that if you write your code with a, you remember, CUDA main copy, and then a kernel launch, and then a CUDA main copy again, these three operations are synchronous. The CUDA launch, the kernel launch is not going to happen until the previous main copy has completed. But there is a way that is using asynchronous transfers and something that is called the streams or command queues in OpenCL, that essentially consist on dividing the total computation that we need to do into different chunks, right? So let's say 4, so that as long as the operation that we need to compute on this input data that we are going to divide is independent of each other, we don't need the entire thing in memory in order to start the execution of everything, but we can, divide into parts, same as we can do, for example, in matrix multiplication, right? In matrix multiplication, you can operate on different parts of the matrix, some rows and some columns, so you could somehow divide the computation, transfer part of the input matrices, start the computation for these input matrices, and then when you are done with that, start with the computation for the second part of the matrices. So essentially doing that is what is called divided the computation into streams, and if we do that, we can overlap the data copy or the transfer with the execution by doing something like this. So as you can see, there is a lot of execution time saving here. You can even calculate some estimates of what's the amount of time that you can save, right? So in this will also depend on what takes longer, right? In this particular picture, we have the data transfer time and the kernel execution time are exactly the same, but usually this or this will be larger than the other one. So depending on that, we will have the data transfer hiding the execution or the other way around. And depending on that, depending on what's dominant, might be the kernel might be dominant or the transfer might be dominant, this will be like, raw estimates of what's the total execution time. And this can be, I mentioned matrix operations, but this can be, for example, very useful for video processing. In video processing, we have a sequence of frames, and we are probably going to operate on each frame individually, or maybe on a window of some number, 32 consecutive frames or something like that. So what we could do is, instead of transferring the entire video or the entire sequence, in this case 6 frames, from the CPU to the GPU and then start the computation, what we can do is dividing the video stream into some chunks of frames that are transferred. We start the computation and we overlap with that, and we can save all this amount of execution time. So this is a very simple example, but as you can see, it's really practical. Okay, so we are done with this first part of the lecture. GPUs as accelerator, it's what we call the traditional accelerator approach, the traditional way of programming heterogeneous systems with CPUs and GPUs. These are all the different things that we have covered. And what we are going to do now is having a very, very short 5-minute break, and then I will give you an introduction to the second part, the collaborative computing part. Any questions? Okay, thank you guys. Okay, let's continue. So, the second part of this presentation, of this set of slides, is the collaborative computing part. As we have just been discussing, the traditional accelerator approach, what we do is that we use this CUDA-malloc and CUDA-main copy to allocate memory. In this case, you have here the input and the output, and to copy the input from the host, that is, in this case, some array called input has been allocated using malloc, copy from this input array in host memory to the D-input array in the device memory, and after that we also allocate the output, and after that we launch the kernel. When we want to make sure that the kernel has finished, we use the CUDA device synchronize, and we copy the output from the GPU memory to the CPU memory. As you can see, I mean, this is not that complex, but actually required some, double programming effort, programmer effort. Why is that? Because we need to double allocate everything, right? We need to not only copy input and output here, but also do a double allocation in the host and in the device, in the host and in the device. So for this reason is why it was originally introduced, or initially introduced, what is called the unified memory. Well, first of all, with previous generation, maybe let's say CUDA 4.0, the unified virtual address space was introduced, and then what was called unified memory was introduced. And this first was for Kepler architecture and CUDA 6, and essentially what happened here is that they introduced one API called CUDA-malloc manage that essentially did this double allocation work for the programmer, right? So actually it reserved some memory space in the CPU memory, some memory space on the GPU memory. But later, with the Pascal architecture, this was in 2016, the real unified memory space, unified memory was introduced. And essentially what this means is that there is a page fault handling, so that the GPU can transparently request memory pages that will be in the CPU main memory, and the data transfer, the movement of these pages from the CPU memory space to the GPU memory space, it will be completely transparent to the programmer. The benefit of this is first that the programming is easier, same as it was in the original unified memory. Second, that we are no longer limited to the GPU memory size, and this is especially important and interesting in the current computing systems because of the era of big data, where we are using all these amount of data to, let's say, for example, train neural networks or analyzing graphs that are from social networks, etc. They are so huge that they might not fit into the GPU memory, even though the GPU memories are larger these days, up to, I would say, 32 gigabytes, but still smaller than the main memory of the CPU and non-volatile memories that are already starting to appear, right? So this can be especially interesting these days for these reasons. Here you can see the syntax, or at least part of it, of this CUDA malloc manage. Instead of having to allocate memory in the host and the GPU, we just simply need to use this CUDA malloc manage, and here, instead of using the CUDA main copy, we just can directly use a simple C main copy to copy, in this case, because we are still doing the double allocation, even though it's not necessary, copying this input into the input, and here also the manage allocation for the output, and we don't need to worry about the data transfer anymore, right? Because the CPU and the GPU can directly use the same pointers, in this case, the input and the output. So both CPU threads and GPU threads can access it. So this is what the unified memory allows us to do. And the benefits of this are going to be that it's going to be possible to have concurrent execution of CPU and GPU working on the same data and collaborating for several reasons. For example, because we want CPUs and GPUs specialized because they are good for different things, right? CPUs are usually good for some sequential computations, GPUs for massively parallel computations. So at some point, our algorithm or our program might have some sequential part that is producing some results that are used by the GPU, and this can be done in a much, let's say, tighter way that it was before, where we need to launch a kernel and then terminate the kernel. We want to make sure that the CPU can read the data and so on. Now it's everything is going to be much more flexible. We are going to be allowed to implement really heterogeneous or collaborative computing algorithms. In the past, the only way that we could do that was doing something like this. Recall that I mentioned before that the kernel launch is asynchronous. So as soon as the kernel is launched, as soon as the GPU thread, the CPU thread launches this kernel, the CPU gets free. So because it's free, it gets free, the CPU thread can do something, some computation while the GPU kernel is running. And at some point, the GPU kernel will finish, and the CPU would have been doing something in the meantime. But this is like, like very, like not flexible manner at all. So there is not there is not much opportunity for concurrency of CPU threads and GPU threads. Now with the unified memory, it's going to be possible to have CPU threads and GPU threads operating at the same time on the same input and output. In this case, we launch one kernel that operates on input and output, and at the same time, we can have the CPU reading from input, writing to output, or even using atomic operations. Why is that? Because the unified memory also implements CPU-GPU memory coherence. So we have memory coherence, so as soon as this output X is modified, the GPU threads will see that modification. We can also use system-wide atomic operations so that if this output X plus 1 is updated by the CPU thread, the GPU threads will also see the right value, right? If they are updating the same memory positions. Question here is, does this have any overhead? Yeah, obviously there is an overhead, especially because this thing can exist, and actually not in Nvidia, but in AMD CPU and GPU integrated systems like the AMD Kaveri, they are operating on the same memory, so the performance is going to be good in discrete GPUs, even though this is, let's say, like a great advance in terms of programmability. There will still be some performance overhead, because every time that we have this CPU updating this value, and maybe a little bit later one GPU thread needs to read this value, we will need to transfer this value, maybe at the granularity of a page or at the granularity of a cache line, from the CPU memory to the GPU memory. So there will be inherently some overhead there, even though this has already improved in the most recent generations of Nvidia GPUs. Here, because this feature is not only available in CUDA, these are the CUDA malloc manage instruction. This is an example of system-wide atomic, how to access some, how to modify some element in the output that actually resides in the unified memory from a GPU thread. But we have very similar constructs for in OpenCL. Its syntax is a little bit more complex, but the functionality is exactly the same. On also other programming languages, this is a higher level programming language, C++ AMP, that can also be used to program these heterogeneous systems. And the use of these new programming features with the CPU, GPU memory coherence and the system-wide atomic operations allows us to have some collaborative patterns. So instead of having, the traditional accelerator model where we have, this could be the first kernel, and at some point all these data parallel tasks are completed, and then we have this coarse grain synchronization that essentially means that both synchronous programming model, the kernel terminates, and then we launch a second kernel. Instead of having this traditional pattern, now it's going to be possible to have different collaborative patterns. One possibility is the data partitioning pattern. In the data partitioning pattern, we assume that we have two devices, device 1 and device 2, and the scenario that we are discussing, these two devices are the CPU and the GPU, but they could potentially be a CPU and an FPGA, or a GPU, FPGA, and CPU, or something like that. Or maybe more than one GPU, different, even with different computing power. And actually, because usually these two devices will be heterogeneous, will be asymmetric, we will have different execution time for, in this case, the first subtask in device 1 takes shorter than in device 2. And when we first subtask has finished, then we have second subtask. It turns out that in this case, device 1 is slower for this second subtask, and then at some point we can still have the coarse grain synchronization, the kernel termination, and then we launch a new kernel. This is what we call the data partitioning pattern. Another possibility is a coarse grain task partitioning. In the coarse grain task partitioning, what we are doing is that one of the kernels is assigned to one device, the other kernel is assigned to the other device. Why do we do that? Because we know that this device is very good for this computation, this other device is better for this other computation. But observe that even though we are still, partitioning the computation in a coarse grain manner, and we have this bulk synchronization in the middle, it's possible to have concurrent execution in device 1 and device 2, because this device 1 could be operating on a different, so during all this time, this device 1 could be operating with this kernel on a previous part of the data, let's say previous frames in video processing. But the good thing, and let's say that the most novel thing that these new heterogeneous programming features allow us to have is this fine-grained task partitioning. And because recall that device 1 was faster for this yellow parallel subtask, while device 2 is faster for this green parallel subtask. It is possible to map all the yellow subtasks to device 1, the green subtasks to device 2, and as soon as device 1 completes with one of these subtasks, it can somehow signal by using, in this case, what we will use are these system-wide atomic operations. We can signal from, for example, a CPU thread to a GPU block or a GPU thread, signal that the subtask is completed, and we can continue with the next subtask. So this is what we call the fine-grained task partitioning. Let's start looking at one example of what we can do with this new feature. So the very first thing is, for example, histogram computation. Let's take this as the very first example. And here what we have is we want to compute the histogram of this image. What we will do is, or what we can do is, divide the image into two parts. Probably we will give the smaller part to the CPU cores because they are going to be slower for this data parallel computation, and the bigger part to the GPU that we have here. We will have the CPU threads updating some subhistogram, the GPU threads and updating another subhistogram, and then we merge both subhistograms, and we might get some performance improvement from doing that, right? Because instead of using only the CPU or only the GPU, we are using more cores, we are using more threads, so more parallelism, and maybe we can get some speed up from that. But still the problem is that, observe that we need, this is the traditional approach, what we will do in the traditional approach, we need to allocate the image in CPU. In GPU, we need to transfer the image from the CPU to the GPU. Then we need to allocate and reset the histogram in the CPU, and then the histogram on the GPU. Then we launch maybe some CPU worker threads. We launch the GPU kernel. When we are done with this, when we have computed this and that, we copy this GPU histogram to the main memory of the CPU, and then we merge them. Right? Maybe we launch some threads, CPU threads, for merging them. Okay, this is something that we can do, but obviously it takes more programming effort, and this is just a toy example, as you can guess, but for more complex algorithms and more complex computation, the improvement, the benefit in terms of programmability might be even higher. So with these new features, what we can do is simply something like that. We allocate the histogram, we reset the histogram, and we launch CPU threads and GPU threads, and they operate, in the case of the GPU kernel using this atomic add system, operate on the same histogram, and we are done. So, yeah, this is for histogram computation. I'm not going to show you performance results for this because, as you can guess, this is very good in terms of programmability, but it's not as good in terms of performance. But it's good for the first example. But I'm going to show you some results for other type of, computation. In this case is Bezier surface computation. I don't know if you're familiar with these Bezier surfaces. They are using computer graphics. They actually were invented by Bezier, who was an engineer in Renault. He was using them to, design, the Renault cars. And essentially what we have here is that we compute the output points of a surface. In this case is this blue thing that you can see in the slide, and the exact values of the output surface are computed depending on some control points. In this case we have a 4x4 network of control points. Depending on where these points are located, depending on what's the relative position of these control points, we will have a different shape of the surface. Here you have the parametric non-rational formulation of this Bezier surface. This is the equation that we need to calculate for each per UV that is each of the output points of the Bezier surface, and these are the Bernstein polynomials that are used for this computation. It's quite a time-consuming computation because you see there are power, we use floating point computation here, so it's relatively time-consuming. The very first, if we want to do this, because you know it's compute-intensive, and if we want to accelerate this, we could say, okay, we might have a not a very powerful GPU, even though this is highly parallel. Maybe your GPU is not that powerful if we are using the GPU in a laptop or in a cell phone. And okay, because it's not that powerful, maybe we can also leverage the CPU cores to run this computation. So in the traditional approach, what we would need to do is doing some kind of a static distribution. We can distribute the output into, so we can divide the output into tiles and assign some of these tiles to the CPU, in this case the green ones, the yellow ones to the GPU. We could do that, and this would give us some performance improvement. This is, you know, some the code for doing this using without unified memory in the traditional approach. Yeah, so the CPU threads operate on some part of the surface, the GPU threads operate on the other part of the surface. When they both finish, they synchronize, and we get the part of the surface that was computed in the GPU memory, and we can definitely get some performance improvement. In this case, these experiments have been run on an Nvidia Jetson TX1, that is a mobile platform, and well, we can get a 17% speed up. What's the problem here? The problem is that we need to profile the system in advance, right? If we want to know what's the exact perfect partitioning of what percentage of tiles, of what percentage of the output surface we assign to the CPU and to the GPU, we would need to try all these or even more and say, okay, this is the sweet spot, let's use 20% of the tiles assigned to the CPU, right? Okay, so that's what we can do in the traditional approach. The good thing is that in the collaborative approach with unified memory, we can do this in a dynamic way, in a more flexible and probably efficient way, by doing some dynamic distribution. As soon as one thread block or one CPU thread finish with computing some of these tiles, go to one queue and takes a new tile and starts the computation. In principle, I mean, this could be a way of implementing this queue by using system-wide atomic operations. In principle, this is not really necessary for Bezier surfaces. Why is that? Because they are regular, very regular computation, right? So as long as we have profiled the system once and we figure out that the optimum, the sweet spot is 20% of the tiles to the CPU, then we are done, and then we can repeat this many times, right? But this might be, or this is actually very useful if the computation is irregular and there might take different amount of time depending on the characteristics of the input or the part of the input, etc. You saw previously some results for a mobile Nvidia system where we use the CPU and GPU in a traditional manner. We can also do the same using the new features. This is for AMD Kaveri, where it's not an NVIDIA system, but we can program it in a very similar way using OpenCL. And you can see here some results from using one CPU, two CPU, four CPUs, CPU threads, and then only the GPU, and then the GPU plus the four CPU cores. It's not that much, but yeah, you can see a little bit of a speed up here from adding the execution of the up to 40%, right? 47% improvement over GPU only. So it's not bad. This is a Similar example, but a little bit more complex. In this case, this is matrix padding. Matrix padding is a simple data reorganization operation that can be useful for some, for example, for memory alignment, and actually when we use SIMD operations can be useful, but also for example, transposition of near square matrices. Yeah, I don't know if you're very familiar with matrix transposition. Data, the matrix transposition, if your matrix is a square, it's super easy, right? Because you just need to swap the elements that are at the same distance of the diagonal. But as soon as your matrix is a rectangle, then it's not that easy anymore. It's really a very complex process, and it's especially complex if you want to do it in place. And doing it in place is actually something that it's desirable in for example, GPUs where the memory, the device memory is not that large, right? We were talking about 32 gigabytes in current GPUs, so it's not that large. So if we want to do a in-place matrix transposition, we will need quite a complex algorithm to do that. The thing is that we can execute, this would be for an out-of-place matrix transposition on the Jetson. In this case, the sweet spot is here in 30%, and we get 29% speed up. But if we want to implement an in-place padding, we will need to come up with some way of synchronizing across thread blocks in the GPU and threads in the CPU. So this is our original matrix. This is how we want it to look. Observe that we have added one extra column, but if we map this or we represent this in the same way as this was represented, it will look like something like this, right? So this is like these cells here correspond to this extra column. And now let's see how we can synchronize, and actually this is something that without the new heterogeneous programming features is something that we can definitely do on CPU, on CPU or on GPU. The good thing is that with the new programming heterogeneous programming features, we can use both CPU threads and GPU threads to operate on this. What would we do? Well, what we are going to do is we will start reading one row. In this case, we assume that we are assigning this row to the CPU and the rest of the rows to the GPU. So we start reading one row because we need to save and some temporary location. And we can have CPU and GPU working in parallel. You see how here, for example, one GPU block has already started reading this row and storing it in some temporary location. Typically, this temporary location, the GPU will be registers or the shared scratchpad memory. We have several threads, several works working in parallel. And as soon as someone has already completed with loading one entire row, it will set one flag and it will start writing to the output destination. Observe that padding means that we will need to move this row somewhere to some highly addressed memory location, starting here. And the good thing is, because we have already set this flag, the in this case, GPU block that is responsible for the next row knows that, because the flag is 1, knows that it can start writing on the output. So as soon as this block finishes loading the row into the temporary location, sets the flag, and because this flag is already set, can start writing, because this block will be sure that it's not going to overwrite these values here, right? It's more clear? Okay, so yeah, that's how this would work. You can see here the entire process, and by using this synchronization, observe that we can actually get very good throughput, actually very high throughput. You can compare, here is the execution for a certain number of work groups, in this case 8, I'm calling them work groups, but because this is OpenCL, but these are blocks, right? Blocks of threads, in this case we have 8, in this case we have 16. So for example, in this configuration with 16 threads, we can, 16 blocks, and maybe we can use CPU threads or not, we can reach very, very similar speed, very, very similar throughput to GPU stream. You might be familiar with the stream that is, yeah, actually Professor Mutlu has talked about the stream. It's a micro benchmark that is used to measure actually what's the maximum available bandwidth in CPU or in a GPU in this case. So in this specific case, we are not getting improvement from using more threads, from using CPU threads in this configuration, but it will also depend on the configuration, will depend also on the algorithm, the particular algorithm. In this case, we actually see some improvement from using some 4 CPU threads in this case. Okay, so I think that it's time to finish because it's already 3 p.m. I will just leave the rest of the slides for you. There are some other interesting case studies for this collaborative computing, and if you eventually want to, you know, take a look at these codes and exercise them a little bit, you might want to access this benchmark suite where you have up to 14 of these collaborative computing benchmarks that can be interesting for you. Thank you very much for your attention. I hope you enjoy the rest of the week.